Okay, now if we apply Ohm's law, remember is V equals IR, and we rearrange it to solve for I, we get I equals V over R, right? So what if we plug in V over R for the I's in each of these equations? All right, so we would get V total over R total equals V1 over R1 plus V2 over R2, it's a 2, plus V3 over R3. Now, what do we know about the voltage in parallel circuits? They're all the same, right? So that means these voltages cancel out. Now, be careful because we don't get R total equals R1 plus R2 plus R3. All of these resistances are in denominators. When we cancel things out, they're replaced by a 1. So really what we've got is 1 over R total equals 1 over R1 plus 1 over R2 plus 1 over R3. Now here's the thing. Historically, students have a hard time using this equation. Right? I know you guys are in fancy math, but still you can forget to do simple things. Right? What we are saying here is that the inverse, right, of the resistances added together equals the inverse of the total resistance. Oftentimes, to get the total resistance, people forget to take the inverse of their answer. So I'm going to change this so that you don't forget to take the inverse. The total resistance, you add the inverses of the 3 resistances of our 3 light bulbs, and then you take the inverse of that. Okay. So here are our 3 equations for parallel circuits: voltage, current, and resistance in parallel circuits. Okay, and then I would like you to also calculate the total resistance 2 ways for this the 3 light bulb circuit as well. Okay, now here is the analogy for the waterfall analogy for parallel circuits. Why is the voltage in parallel circuits the way it is? Why are the voltages all the same? So again, if you think about voltage, like the energy, potential energy of electrons, and we'll do an analogy for a waterfall. Let's say we've got a, let's say we've got a big ol' waterfall. Okay, so say we've got a cliff, and at the bottom of the cliff, there's a pool, right? Okay, and then there's a river that is coming towards the edge of the cliff, and the waterfall, there are like rocks here, rocks on the cliff. And so the water gets split into 3, the total water gets split into 3 separate waterfalls, right? So we can see that the total current that's coming in, right? So this is I total, and then it gets split into 3 pieces: I1, I2, and I3. But they're all starting, each of those 3 waterfalls is starting with the same potential energy, and all 3 of those individual waterfalls are ending up with 0 potential energy at the pool below. Okay, so they're all losing the same amount of energy. And if we start off with 9 volts of voltage from the power supply, when the current goes through one branch versus another, no matter where that current ends up, like what path it takes, it's going to end up right here. At this side, there are no more resistors, there are no more light bulbs. All of the paths have to end so that the electrons have 0 volts of potential. Okay. All right, so we already talked about potential drops. I need to mention an idea called electron drift speed, because you might be thinking, well, after the electrons go through the last light bulb or the last resistor in our circuits, they've got 0 energy, right? So do they stop, right? Why are we even seeing current in the circuit after the electrons go through the last light bulb or resistor? Well, they're actually traveling at a constant, what's called drift speed. It's a constant speed. It takes into consideration the total resistance of the circuit and the potential difference. And so they're actually not speeding up or slowing down as they go through the circuit. Okay, so the electron drift speed equation is written in kind of a weird way. So we've got I, and this is in your data booklet for your reference in topic 5. I is a current that's going through the wire. N is the number of electrons per meter cubed. Okay, so it's kind of like the electron density in a wire. A is that cross-sectional area of the wire, capital A. Okay, so again, if you take a wire and you slice it, the cross-sectional area is the area of the circle if you're looking at the very end of the wire. Lowercase v, right here, that's the average electron drift speed. So it's that the value of that constant speed on average that the electrons are traveling at in meters per second. And then Q, sometimes written as lowercase e, here is the elementary charge, right? 1.6 times 10 to the minus 19 coulombs. All right, the charge of an electron. Okie dokie. All right, so that's how you can find that constant speed or the electron drift speed that electrons would have in that particular circuit. All right. Cool. Now I've got one more thing that I want to talk about, and that is power in circuits. Okay, so just like if we're talking about energy use, right? Power is in watts. Which is a joule per second. So we're talking about energy used per second. And what is using energy in a circuit? Well, it's whatever's providing resistance, right? It's an appliance, a light bulb, or a device that's called a resistor. Okay, so it depends on the power that's used, depends on how much energy, right, the circuit has in the first place, what the voltage is. It depends on how much current is running through a resistor as a result. And so there are actually 3 ways that you can write these equations. So again, the general equation for power is work done, or the change in energy per unit time. Okay. For electric circuits, there are actually 3 equations. Power equals current times voltage. Oh, hey, in this video, I'm down in the little corner. Hey, didn't know you were seeing my face, you guys. All right, now this is kind of our base power equation. And if we used Ohm's law over here to the side, V equals IR, right? What if instead of writing V, we plugged in IR? Then we would get power equals I squared R, right? Because you'd have I times IR. Okay. Then what if instead we plugged in to this equation for I. We rearranged Ohm's law to be written as I equals V over R, and we plugged in V over R in here. So now we'd have power equals V times V over R. Okay, so this would be V squared over R. Do you see how I did that? I plugged this in here and I had V times V is V squared and then all over R. Okay, so these are our three equations for power. And you know how I remember them? There's a physics song that's actually sung to the tune of Twinkle, Twinkle, Little Star. Are you ready? I'm going to sing it for you. I am not a singer, by the way. This is something that occasionally my daughter requests because it's just nerdy fun and she doesn't really know what it means, but someday she will, and she'll be like, I know physics. All right, are you ready? Okay, so twinkle, twinkle, little star, power equals I squared R, up above the world so high, P is equal to V times I. Twinkle, twinkle, little star, P is V squared over R. Okay, so now you guys can go sing that to your folks. All right, kiddos. When we talk about the power that is used in circuits, we oftentimes call it power dissipated. And that's just another way of saying power used. All right, kiddos, that's the end of the lesson today. I will post some problems on the Google Classroom for you to try. And don't forget to finish up your light bulb lab before the asynchronous class on Thursday. All right, I'll see you soon.